We are now entitled, or we are now well poised to look at the Haar filter bank in the frequency domain. And what do we mean by the frequency domain? With mod z equal to 1 or z equal to e raised to the power j omega. Indeed, consider the analysis side, the analysis filters. Both of them have a frequency response, obviously. Let us take the filter 1 plus z inverse by 2 and let us look at its frequency response. Of course, we would obtain the frequency response by substituting z equal to e raised to the power j omega. And that would give us 1 plus e raised to the power j omega by 2 minus j omega by 2 if you like. Which we can simplify. We can take an e raised to the power minus j omega by 2 common here and then put e raised to the power j omega by 2 plus e raised to the power minus j omega by 2 inside the bracket and leave the half factor as it is. So, this is what we have here. Now, recognize that this is essentially 2 times cos omega by 2. And therefore, we have half e raised to the power minus j omega by 2 times cos omega by 2, which gives us e raised to the power minus j omega by 2 times cos omega by 2. This is the frequency response. Let us sketch the magnitude and the phase of this frequency response and recall that for discrete systems it is adequate to sketch the magnitude and phase, or for that matter to determine the magnitude and phase response in the region omega going from minus pi to plus pi. We do not need to go outside that range, because after all the frequency response is periodic with a period of 2 pi. So, whatever occurs between minus pi and pi is going to be repeated around every multiple of 2 pi. So, the magnitude of this response would be mod cos omega by 2. And let us confine, as I said, to omega between pi and minus pi, whereupon cos omega by 2 turns out to be non-negative. In fact, essentially cos omega by 2 is real and greater than equal to 0 in this region. Thus, phase contribution from this term is 0. So, if you look at the overall frequency response here, namely e raised to the power minus j omega by 2 times cos omega by 2, this has no phase contribution. For minus pi less than equal to omega less than equal to plus pi, and the phase contribution comes only from here. The phase contribution from this term is going to be equal to minus omega by 2. So, now we can sketch the phase and magnitude contributions very clearly. Let us sketch the magnitude response. the magnitude again, this is a real filter. This is a filter with a real impulse response. Now, when an impulse response is real, the frequency response is conjugate symmetric. So, whatever is at omega is also at minus omega in magnitude, whatever is at omega in phase is the negative of what is there at minus omega in phase. So, we need only sketch the magnitude response and the phase response between 0 and pi. We can ignore minus pi to 0 because there is going to be conjugate symmetry. So, let us sketch it only between 0 and pi. You can see that this is the kind of pattern that it is going to show, essentially of the form cos omega by 2. And for the moment, we can already see that this is something like a crude low pass filter. I say it is a low pass filter because it emphasizes the lower frequencies and de-emphasizes the higher frequencies. I say it is crude, it is far from ideal. In fact, if you had an ideal low pass filter, then of course, you need to specify the cutoff too. So, an ideal low pass discrete time filter with a cutoff of pi by 2 would look something like this. I mean, in the magnitude sense. So, it would have a magnitude response that looks like this. And ideally, the phase response would be 0. So, it would be 1, the response itself would be 1 between 0 and pi by 2 and 0 between pi by 2 and pi, and of course, mirrored as it is between minus pi and 0. So, ideally, we would have this magnitude and phase equal to 0. Where are we in reality? We are trying to replace this ideal filter here with this crude approximation to the low pass filter here. So, please remember, this is the ideal towards which we are striving, and this is where we have reached in some sense with this very simple Haar multi-resolution analysis or Haar filter bank. Now, we shall understand this even better when we look at the magnitude response of the high pass or the other filter in the filter bank. But for the moment, let us complete our discussion by also drawing the phase response. So, the phase response of this filter is as follows. The phase response, as we noted, was minus omega by 2. So, in the region from 0 to pi, at pi it would of course take on the value of minus pi by 2, and this is a straight line. So, in fact, you get what is called linear phase. Now, linear phase is something very attractive in discrete time signal processing. In fact, one of the reasons why people go to discrete time signal processing from analog signal processing is because you can get linear phase. Why is linear phase important? Let us spend a minute in reflecting on this. You see, what does the phase response denote? Or for that matter, what does the frequency response denote? The frequency response tells us what happens to a sine wave when it passes through the system. So, in fact, to understand this better, let us go to continuous time first. Suppose we fed a sine wave, let us say cos omega naught t plus phi naught times a naught. So, amplitude a naught, frequency capital omega naught, phase phi naught, to a continuous system, to a continuous time filter. With frequency response let us say h as a function of omega, what would come out? Very simple. You would evaluate the frequency. This is of course a complex number as a function of capital omega. You would evaluate this at omega equal to omega naught. The magnitude would multiply the magnitude, the angle would add to the angle here. So, in other words, what would come out is mod h evaluated at omega naught, a naught cos omega naught t plus phi naught plus angle of h evaluated at omega naught. What is the effect of this angle? As you can see, the effect of this angle is to change the phase, and a change of phase is equivalent to a change in time. So, it is like shifting the time, shifting the sine wave on the time axis. So, angle h omega naught essentially shifts the sine wave, shifts the sinusoid by t is to be replaced by t plus something, and that plus something is given by this divided by omega. So, I mean let us write it out explicitly that way, let us reason out what it should be explicitly. So, we will rewrite that expression, we will write it as mod h omega naught times a naught cos, we will keep phi naught as it is, we will take omega naught common, and then we will write t plus the angle of h omega naught divided by omega naught. I am sorry, yeah, well, I will write omega naught t plus this into omega naught. So, again you have angle here. So, this into omega naught, I will write it this way. So, now I can rewrite. So, forgetting about this part, see this part is essentially a change of magnitude, it is only this part which I wish to focus on. T has been replaced by t plus angle h omega naught by omega naught. So, essentially this quantity angle h omega naught divided by omega naught is like a time shift, is that right? It is an important observation we make. Now, just in case it is independent of omega naught, we have a good situation. So, this time shift actually is what is called a necessary evil in the frequency response. Most of the time when we give specifications for designing a filter, whether it is in the analog domain or in the discrete time domain, we do not really want a phase response. The phase response comes as a necessary evil and we have to work around it. Now, what does the phase response do? At each frequency, it creates a time shift. The phase response creates a time shift dependent on frequency. What is a good situation to have? An ideal situation is no phase response. This is unachievable. In fact, it is unachievable because of causality. If you want the filters to be causal, then you cannot ask for 0 phase. Incidentally, that is why you can use 0 phase filters in dealing with images, in dealing with 2-dimensional data. Because in 2-dimensional data, causality is not an important requirement. But when you are dealing with 1-dimensional data in time, causality is essential, you cannot avoid it, and therefore, you cannot avoid a phase response either. Now, if you must live with a phase response, what kind of a phase response would you like to live with? You would like to make sure the phase response does not treat different frequencies differently. So, if it has to shift a sine wave in time, so be it, but then shift all sine waves by the same time, and that is exactly what we are saying when we talk about linear phase. Linear phase means angle h omega naught by omega naught is independent of omega naught. That means, it is a constant. Let us say it is some tau or tau naught if you like, which means that the angle of h omega naught is of the form some omega naught times tau naught. It is linear in tau naught, in omega naught. That is why it is called linear phase. Now, this is what I am trying to emphasize at this point. This very simple filter bank, the Haar filter bank, has this beautiful property of linear phase. By the way, this is something unusual in filter banks. It is not easy to design filter banks of larger order with linear phase. In fact, only one class of filter banks has this property. Linear phase in some sense has to be compromised with something else. So, in the Haar you can have your cake and eat it too. So, you can have linear phase, you can have orthogonality. But later we will see that if you want to get something else out of your filter bank, if your filter bank must be better in some sense, you have to sacrifice linear phase.